Hi, this is Sman Chowdhury, and in this video you will learn about the relationship between the graph of a function, the graph of its first derivative, and the graph of its second derivative. Thank you. First, let's go over some basic rules. If a function is increasing, the first derivative is positive and will be above the x-axis. If the function is neither increasing nor decreasing, it will have a horizontal line, making the first derivative equal to 0. This is true because the slope of a horizontal line is always 0. And this is where the function will intercept the x-axis. And lastly, if a function is decreasing, the first derivative is negative because the slope is negative, and the function is below the x-axis. Next, if the function is concave up, the second derivative is positive, and when the second derivative is positive, that means that the first derivative is increasing in value. And if the function is concave down, the second derivative is negative, and when the second derivative is negative, that means the first derivative is decreasing in value. Now let's analyze these two curves. First, we have concave up. On the left, the function is decreasing, so let's say at this point the slope is approximately -1. Then at the bottom, the slope is 0 because there is a horizontal tangent. And then at the right, the function is increasing and is approximately 1. So notice that when the second derivative is positive, the first derivative or the slope is increasing in value, which is seen as the function goes from -1 to 0 to 1. Now let's look at the second curve, which is when the function is concave down. At this point, the function is increasing, so it has a positive slope. Let's say it is 1. At the local extrema value, or the local maximum, there is a horizontal tangent line, which means that the slope is 0. And then at this point, the function is decreasing, and let's say it has a slope of -1. So notice, when the second derivative is negative, the first derivative or the slope is decreasing, which is shown as the function goes from 1 to 0 to -1.
So now we're going to look at some examples. The first one I'm going to use is f of x equals sine of x. So first, you always want to draw your graph and label everything. And just draw your graph. So now you first take the derivative of the function, and the derivative of sine x is cosine x. And you just once again draw your graph and label everything. So now let's apply the rules that I first outlined. So first we have to see where our graph levels, which means where does it have a horizontal tangent. And we can see that at pi over 2 and at 3 pi over 2, our graph has a slope of 0, which means on our derivative graph at pi over 2 and 3 pi over 2, our function will intersect the x-axis. So now let's look at the first interval, from 0 to pi over 2. We can see that the function is increasing because it has a positive slope. And that means that because it has a positive slope, it will be above the x-axis on our derivative graph. And this is how that will look. Now let's look at the next interval, pi over 2 to 3 pi over 2. Here we can see our graph is decreasing because it has a negative slope. And from here to here, our graph is increasing much faster and then increasing much slower. That means we will have a curve below the x-axis, like this. And our next interval is 3 pi over 2 to 2 pi. And our graph is once again increasing because it has a positive slope. So it will be above the x-axis on the derivative function, and it will look like this. So now you have to go through the same process when graphing the second derivative. So first, let's take the second derivative, which is negative sine of x. And let's just draw our graph and label everything once again. So first, let's see where our graph levels. In other words, where does it have a horizontal tangent? And we can see at pi we have a horizontal tangent and the slope of the function is 0. That means on our derivative graph at pi, the function will cross the x-axis. So first let's look at our interval 0 to pi. And we can see that it is decreasing and has a negative slope. And that means it will be below the x-axis on the derivative graph. And this is how that will look. So the next interval is from pi to 2 pi. And here our graph is increasing and has a positive slope. That means it will be above the x-axis, and this is what it will look like. So now you can see that it is just one process that you have to keep repeating. So first you have to see where you have horizontal tangents, where your graph has a slope of 0, because that is where your derivative function will intercept the x-axis. Then you look at individual intervals to see whether the graph is increasing or decreasing. And if it's increasing, the derivative function will be above the x-axis, and if the original graph is decreasing, the derivative function will be below the x-axis. And you just repeat this process when going from the first derivative graph to the second derivative graph. So let's try another example. This time I will use f of x equals x cubed. So as always, you just want to draw your graph and label everything. So from this we have to draw the derivative graph. So let's first take the derivative, which is equal to 3x squared. Now let's just draw our graph once again and label everything. And you always want to make sure you have the same x values, just so it's easier for you to draw your derivative graph. So just looking at the graph, we can see that from negative infinity to infinity, our graph is always increasing. It always has a positive slope, which means that on our derivative graph, it will always be above the x-axis. However, here the graph is increasing much faster compared to here, and then increasing much faster again. So that means this is how our graph will look like. A sharp curve above the x-axis, because although it is increasing faster and slower and faster, it is still increasing, and thus it will still be above the x-axis. So now the same process takes place for our second derivative graph. So let's take the derivative first, which will be 6x. And once again, just draw our graph and label everything. So we can see that our first derivative graph is a parabola, which indicates that our second derivative graph will be a linear function. So let's look at the first interval. So first we determine where the graph levels, which means where does it have a horizontal tangent where the slope equals 0. And we can see that that occurs at the x value of 0. That means our graph will intercept the x-axis at the origin. So let's look at the first interval. From negative infinity to 0, we can see that the graph is decreasing and has a negative slope. That means it will be below the x-axis from negative infinity to 0. So this is how that will look like. Next we look at our second interval from 0 to infinity. And we can see our graph is increasing and has a positive slope. That means from 0 to infinity, our derivative graph, our second derivative graph, will be above the x-axis. And this is how that will look. Now let's try a final example where you will not be given a function, but rather just a graph. So I'm just going to draw a random graph, and of course label everything. So this is our parent graph. Now let's draw our derivative graph, our first derivative graph. So of course you just want to label everything once again, and make sure you have the same x values, just so it's easier for you. So first we have to see where we have horizontal tangents on our original graph. And we can see there's one at x equals -2 and x equals 1. That means on our derivative graph, the function will intercept the x-axis at x equals -2 and at x equals 1. So now let's look at our first interval from -4 to -2. And we can see our graph is decreasing because it has a negative slope. That means from -4 to -2, the derivative function will be below the x-axis, and this is how that will look. Now let's look at the next interval, from -2 to 1. And here we can see our graph is increasing because it has a positive slope. That means our derivative function will be above the x-axis from -1, from -2 to 1, and this is how that will look like. And finally, let's look at our last interval, which is 1 to 4. And here we can see that the graph is once again decreasing because it has negative slopes. That means from 1 to 4, our derivative function will be below the x-axis, and this is how that will look. So now let's do the same process for our second derivative graph. So first, you just want to draw the graph. So first, we once again see where our graph has horizontal tangents, and we can see there's one at x equals -3, x equals -1, and at x equals 3. That means on our second derivative graph, the function will intercept the x-axis at x equals -3, at x equals -1, and at x equals 3. So let's look at the first interval from -4 to -3. It is clear that the graph is decreasing because it has a negative slope. That means on our second derivative graph, the function will be below the x-axis from -4 to -3, and this is how that will look. So now let's look at our next interval, from -3 to -1. We can see that the graph is increasing because it has positive slopes, which means that on the second derivative graph,
The function will be above the x-axis.
and this is how that will look. Now let's look at the next interval, which is from -1 to 3. And we can see that the graph is decreasing because it has a negative slope. That means on the second derivative graph, the function will be below the x-axis, and this is how that will look. And our last interval is from 3 to 4. And we can see that the graph is once again increasing because it has a positive slope, which means on our second derivative graph, the function will be above the x-axis, and this is how that will look. And there you have it. This is how you graph the first derivative graph and the second derivative graph based on their relationships to the original graph.